What's up, scholars? Today we're talking about inverse trig, but before we do that, I want to show you this very cool GIF that I found. All right, so check this out. This walks around the unit circle and graphs out its x value everywhere. That's what the graph at the top is showing you, the x value as this traces around. And the blue graph here is the y value as this dot traces around unit circle. And as we talked about before, but now it might make more sense, the cosine of theta as we walk around the circle is the x value, and the sine of theta is the y value. So very cool to see things graphically like this. This website has some great GIFs. I'm going to show you two more. This one here is demonstrating what a radian is. A radian is the length of a radius mapped onto the outside of the circle. Voila! And how many radians would it take to go around a circle? Well, the around a circle is the circumference, right? And we know our circumference is 2 pi r, so there are 2 pi numbers of radians we would need to use to walk all the way around the circle. And finally, this last one I want to show you has all 6 trig functions mapping out here as this dot is walking around the circle, but I want to pay close attention to where sine and cosine and tangent are positive. So right here, cosine is positive, and right there, cosine is positive. So cosine is positive in the first and fourth quadrant, which makes sense because cosine is the x value and x is positive in first and fourth quadrant. Sine, on the other hand, is positive when y is positive. So sine's going to be positive in the first and in the second quadrant. And tangent is sine divided by cosine. So tangent is positive when both are positive here in the first quadrant, and tangent is positive when both are negative here in the third quadrant, because a negative divided by a negative is a positive. All right, let's go write that out. So we're answering the question, where are sine, cosine, and tangent positive? We've got the first quadrant, second quadrant, third quadrant, and fourth quadrant. Great. Well, we said sine is the y value. So sine is going to be positive in the first quadrant where the y value is positive, and the second quadrant where the y value is positive. Now, cosine is the x value. So cosine is going to be positive where x is positive, namely in the first quadrant and the fourth quadrant. And tangent is sine divided by cosine. Sine theta divided by cosine theta. So that's going to be positive where both of these guys are positive or where both are negative. So positive divided by positive is positive, and negative divided by a negative is positive. So tangent also positive in quadrant 1 and in where both of them are negative, quadrant 3. So there's a quick little mnemonic device you can remember if you go around counterclockwise, quadrant 1 to 2 to 3 to 4, where all are positive, sine is positive, tangent is positive, and then cosine is positive in quadrant 4. All right, so I said we were talking about inverse trig functions. What are inverse trig functions used for? What are inverse trig functions used for? They are used to find the theta. Find the theta. So let's say, for example, I know that the sine of theta is equal to 1, but I want to know, where does this happen? I want to find for what thetas this is true. Now, recall very quickly our use of inverses in the past, which you may not have known you were using an inverse, but you were. So if I had a very simple equation, 2x equals 10, that's saying 2 times some number is equal to 10. To get that x by itself, to solve for x, I'm going to do the inverse operation of what's happening to it right now, namely division. Division is the inverse of multiplication. So we divide by 2 on both sides and get x by itself. So here we need an inverse operation to get this theta by itself. Our inverse operation for sine is going to be sine inverse. We'll take the sine inverse of both sides, just like we divided by 2 on both sides. So sine inverse looks like sine to the -1. When we do that, these cancel out just like those 2's cancel out, and I'm left with just the theta. So theta is equal to sine inverse -1. Et voila, that's the answer, right? I mean, not exactly. We've arranged it so that we could plug it in somewhere and find the answer, though. Okay, before we plug this into a calculator, I want to build some intuition here and look at this graphically. So I have plotted in red here, f of x equals sine of x. I already changed the units to radians. If I would have changed this to degrees, it would only repeat every 360 degrees. So this thing would be way too spread out. So let's keep it in radians so that it repeats every 2 pi. That's the unit or the period for this sine function here. So we said we were looking for, where does sine of theta equal 1? Well, another way I can answer this question is make a horizontal line through 1, and everywhere it intersects, that's where sine of x is equal to 1. So as we see, we've got an answer here, 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 we've got an answer here. Uh-oh, we should see a problem. We have infinite answers. This is a periodic function that repeats forever. So there are infinite answers to this question of where does sine of x equal 1? So we have to restrict where we're asking for answers to come from. We're going to restrict our domain to one cycle, one circle, or one walk around the circle, one period. So one period for this guy would start at the 0 and go to 2 pi. That's how long it takes for this cycle to repeat. Oh, now we only have one answer here where f of x equals 1 intersects sine of x. So sine of x equals 1 at only one place, which is this pi over 2, which we may remember is 90 degrees. So the whole point here was we had to restrict our domain, just find answers in a certain space, because otherwise we would have infinite answers, which is too many answers. All right, now let's go plug this into a calculator using everybody's favorite math way. Let's solve for this in degrees. Solve for this x in degrees, plugging in x equals inverse sine of 1. And look, it says x equaled 90, which is what we said. It was going to be pi over 2 or 90 degrees. Excellent. So what we just found for theta between 0 and 360, 0 and 360, theta equals 90 degrees or pi over 2 radians. Awesome. All right, so I want to do one more example. Let's say we've got sine theta is equal to negative square root of 3 over 2, negative square root of 3 over 2. Now let's go back to our Desmos and see graphically where this is going to be. So we've still got our sine of theta going to equal negative square root 3 over 2. Gotcha. Let's restrict our answers again to one cycle, one period. So we're going to keep our answers between here and here. And we're looking for where our red line intersects our green line, which will be at 4 pi over 3 and 5 pi over 3. Now that negative 0.866, that's what you get when you do negative square root of 3 over 2. So our answers here are going to be 4 pi over 3 and 5 pi over 3. We could use these right away and just convert them into radians, which would not be a bad idea. So let's ask Google to convert radians to degrees for me. Should pull up a nice little calculator. Awesome. So we said 4 pi over 3. That's going to be 22.9 and change. It's kind of nicer being in radians, I would say. I'm just gonna keep 2 decimal points just in case. And 5 pi over 3, 286.4789. All right, we could have also plugged this into our good friend, the math way. So let's see what we get here when we plug this guy in. Yikes, I realized I messed something up when I was looking at my conversion. It didn't include pi, so I had to find a new calculator to convert radians to degrees. So 4 pi over 3 radians is 240 degrees. Great. And 5 pi over 3 convert. There we go, 300 degrees, much better. 300 degrees, so 240 and 300 degrees. Excellent. So when we plug this into the math way, and it tells us that our exact value is x equals negative 60 degrees, why does that make sense? Why does that make sense? So if we go back in here, Mathway tells us it's negative 60 degrees. Negative 60 means we're going in the clockwise direction. So negative 60 degrees here, negative 60 degrees. So well, that is going in the counterclockwise direction, 300 degrees. Ah, okay, great. We got that guy. But where did the other one come from? Well, we know sine is negative. This guy, sine is negative, where y values are negative, which are in the 4th and 3rd quadrant. So we know we need to have another answer somewhere here in that 3rd quadrant. So if we make a right triangle off this axis and think about what sine is of this negative 60 degree angle, it's opposite over hypotenuse. We'll have the exact same value with a negative opposite. I made that look like a theta. It should be an O. Negative opposite over hypotenuse right on the other side over here. If this was negative 60 on the other side, it would have a negative y value still. I'm making it a colored in 0 or O for opposite. And hypotenuse. These are the same. These are going to give us the same value for sine. They have a negative y value here for the opposite side over the hypotenuse. So now we just need to figure out what is negative 60 degrees from this axis. Well, that's 180 degrees plus 60 more degrees. That's where we get our 240 degrees right here. All right, cool. That is your intro to inverse trig. So we talked about where sine, cosine, and tangent are all positive. All of them are positive in the first, sine in the second, tangent in the third, cosine in the fourth. We talked about what are inverse trig functions used for. They're used to find the theta. For each of your trig functions, you're going to use your inverse, which is like to the -1. So for sine, we use sine inverse sine to the -1 to get our theta by itself. And then we can either plug into a calculator or look on our Desmos and do this graphically. So graphically, when we were looking for where is sine of theta equal to negative square root of 3 over 2, we found was 4 pi over 3, which we could convert, be careful, we could convert to degrees. We could also use our Mathway calculator and figure out what the other degree is going to need to be based off of drawing our trig triangles here. Now, the same concept is going to be true for cosine and tangent. All right, scholars, love you so much. Do your best and keep on that hustle.